Good afternoon, everyone. Let's continue with the next section. So last video we talked about based on shared memory, we can perform the inter-process communication. So for here, we want to talk about the other one, which is based on the message passing. Okay. So maybe you ever use this one before. For example, like you use a socket for the communication between two computers you want to communicate. For example, one is the client, the other one is the server. Okay, in fact, that is based on the message. Okay, that's the belonging to this type of communication. So that means there's one process which is running on the server, and then there's another process which is running on the client. So each one, so this one, the server, there's a process which provides data services. There's a process which is listen to this, whether there's a, for example, there's a point, we call it a port. Okay, so based on the socket, it means it's IP address, and then it's port number. This is socket. So that means it will identify this type of service provided by this server. And there's a process which is listening to that port, that socket. And then you send a request to this socket, so it will receive the message and then find the information and then send the message back to the client. So this is one type of message passing, because we don't have a shared memory card. So sometimes it's not possible. This is like a distributed computing system. Okay, so that means a computer system. So we have to use the message passing. Okay, let's look at details for here. So this is the mechanism for process to communicate and to synchronize their actions. Of course, this means there's another one is based on shared memory. That is, the unit is within one computer system, which is their uniform systems. For example, operating system is only one, or at least the same, and then they can it's easy to share the memory. So they can have maybe a storage network to access. Each of them can access that file. But if it's a network of computer systems, usually they contain the different computer nodes. Each one is running different operating systems, and then we have to use message passing. Okay, so if you have learned the network, some networking class, computer networks, so it will mention about how can we communicate between different nodes within a network. So that's the similar idea. We send a message, sometimes we call a packet. So in a packet we have a header and the message contents and the ending. So, and also maybe have some IP address. You want to send this packet to another computer which must have the IP address and also which port number, so like this. So okay, so but that will be a different course. So here we talk about mainly about you can think about the network operating system. How can we perform the message, perform the inter-process communications? So we can use the message passing. So message passing is a process communicate with each other without reporting to shared variables, because we don't have data shared variables. And basically we perform the message passing based on these two operations. So in the past I mentioned we will use some system calls. So shared memory so is different. So that means you need to control how you will share that memory. So the operating system kernel will not have any control on this one, but this one is different. You must use the system call. Okay? Based on some function, you can send a message. You may have a message queue, but you still need to use some system call. How to send a message to a message queue? How to consume or extract a message from a system message queue. So basically, we have two. Here is just like, of course, in different operating systems, they will implement in different ways. But here it's just like you need to know, okay, we have these two operations. One is like you want to send a message to to another process. The other one is like we want to receive a message from another process. So it's this is considered how you send must have a receive. So that means this is the two operations we have. And then inside we said that of course this is like abstract definition. So it just got a message. So the message we have two different configurations for this one. You can fix the size. You can also have a variable size. So that means of course it's not flexible if we fix the size, because sometimes it's waste, sometimes it's not a must. Maybe your message is too big, too long, you cannot send it via one message. So that means it has cause troubles, because once the message is routing on the network, some message may have some network issue that may routing slowly, and then maybe arrived early message maybe arrive later. So you need to combine sort the order as well. So rather than like that, we may prefer a variable one. So that means the message can be changed, size can be changing depending on the needs. Okay. So here when we design, for example, if we want to design a message passing mechanism, we want to consider a lot of things. So this is the consideration we want to have. For example, assume process P and Q which communicate. First one is that these two processes must have a communication link. If it's networking, they may use some different layers, because when we talk about the network, we divide it into maybe 7 layers or 5 layers. So that means we use different protocol to communicate in the comparable layers. So this is the same idea. That means the link sometimes is a logic idea. It's not like a really physical one. Okay, we must buy a cable, because even one physical cable can have a lot of links. Link means what is the starting, what is the ending, right? Or you can what is the sender, what is the receiver. So this is the most important thing, and then they know each other. So this is the idea. So establish a communication link between them, and then exchange message via the two operations, send and receive. So when we design this message passing system, we need to think about these issues. So let's go over it quickly. For example, how can we establish a link? Okay, so this involves networking issue. If within one computer system, maybe it's easy. You can just use a different port, because if in one computer you can the same IP, so you use different ports to represent. Okay, this is for process, sender process. This port number is for the receiver process. But if with two different computers in a network, you need to know the IP address as well. Otherwise, you cannot find a computer. Only know the IP address, but the IP address only has maybe a lot of services. For example, for the server, so you need to use the port number to differentiate. Port number is also a logical concept. Just want to differentiate different services provided by a server, or just like a different processes running on a client. Okay. And the next one is whether we can allow two processes, more than two processes associated with one link. So this is like this. That means I send this one, whether we can get like this broadcast in, of course in the networking course you also maybe know we do have that broadcasting protocol. Okay, you don't need to send a one-to-one. You can just send a broadcast message, and each one will receive the message. That's possible. Okay, that's also possible. So that means that you can decide accordingly whether if you do like this one, you need to confirm, for example, each of them receive the message, whether they will acknowledge the receiving. So that means, for example, send a notice to the sender, I received each one. Or for example, if you broadcast, it's like the message is only received by one or by all of them. So we also need to consider this design. And the next one is how many links. For example, between any two processes, how many links do you allow? Okay, so just like two cities, you may have multiple roads, okay? So that means that you only want to have one, or just have multiple. Of course, uni maybe it's enough to have only one unique link is already enough. But sometimes maybe you need to have multiple. Okay, depends. And the next one is what's the capacity of a link? Capacity means for this link, how big size of the message you can send. Okay, and then next one is the size of the message that link can accommodate fixed or variable. So whether you can allow a fixed size only, or you can allow a variable size, variable length message to be sent. And then the other one is whether it's unidirectional or bidirectional. Unidirectional, that means it's only like one direction. You can only send, and then maybe you have another link which is only receive. Or you can just establish one link can both send and receive. So this one seems simple. So one is send, the other one is receive. There's no conflict. But this one has a problem, correct? One is send, at the same time you can also receive. So is there any problem? Because of course one link at one time can only do one thing, correct? Because the message is transitioning along the links. So this one you also need to consider. Okay, if there's conflict, how can you solve? Usually we use bidirectional, okay, but you still need to consider maybe just the solving the conflicts issue. So different operating systems will implement this one in different way. This is especially important in a distributed operating system, okay, or network operating system. So next one we want to talk about the implementation of the communication link. Okay, communication link. So for here we can have different looking at it from different aspects. Physically we can use what is the method, and logically we have which operation, which options. So physically is for example you can use shared memory is possible, okay? For this link you use a message queue. You could create a message queue in that shared memory, but this is not the same as that shared memory based IPC, because this is not you are able to access the memory directly. You just send a message and save in that shared memory. It's just like you have a mail, cut, and then the postman put the mail in your mailbox, and then you get the mail from there. So this is shared memory. So it's not like you can connect with the postman directly. Okay, so send a mail to me, and okay, you can request. So this is the file, the shared memory. Okay, so you can find many maybe design is also coming from our practice, okay, practice or daily life. So sometimes do not think it's something is very sophisticated. Sometimes it's just borrowing from our daily life. For example, later when we talk about some process synchronization is also same. In fact, we borrow some mechanism with a signal, but that mechanism is really the same as the railway station. So for example, two trains, how to avoid they will have a conflict between the running, right? So we schedule like this. So each time we can only allow one to pass that one, and then we signal. We allow another one to pass that joint. So same idea. We borrowed from that daily life practice. And then you can also use a hardware bus. So link bus, if it's only within one computer system, you can use the bus. Bus, of course, this is like a data transfer bus, not really bus. So the hardware bus is allow you to send a message, send the data from one to the other one. You can also maybe network. If it's a distributed computer system, maybe you have this So it really depends on the application. Okay, whether it's within one small computer system or you can use these two. You also can use network if it's a distributed system, network system. And logically, we either this one doesn't matter, but we may have different options, direct or indirect. Okay, indirect. So that means later we'll talk about what is direct and indirect. So that means whether you can communicate with a receiver, sender directly, or you need to file some other thing, for example, a mailbox. Okay, and the synchronize and asynchronize. This is maybe it's the first time we point out this idea, synchronize, what it means for synchronize and what it means for asynchronize. And then we have automatic and explicit buffering. So that means this one we talk about the buffer size, whether it's no buffer or limited buffer or unlimited buffer. Okay, let's look at the first one is the direct communication. So we don't spend our time in learning the physical one because that will depend on the implementation and so on. And but logically we have these things. So we talk about direct and indirect. So direct you can find it here. For example, one process can send a message to a process P. So you must point out which process you want to send. So P and which message. And then a process can receive message from process Q. So that's now you establish the relationship. Okay, so that is Q to P. Okay, so Q, this is Q, send a message to P, and P receive a message from Q. So this is the basic idea. So you now establish this send and receive relationship communication mechanism. And then for this one, because you already point out the receiving or the sender or receiver's message, so the links will be established automatically. You just need to call the two functions which are system calls, and then they will find the process because you know each process has a process ID. Okay, then they will find it. So it's automatically. And then a link is associated with exactly one pair, like from Q to P. Between each pair, there exists exactly one link. Okay, there is one link. The link may be unidirectional or bidirectional. So you can allow both. Okay? So that means this establishes the relationship between P and Q. They can send a message whether you can only allow one direction from Q to P, or you can do both from P to Q, Q to P. Okay. And then indirect communication is different. So for the previous one, you can find we use process ID, okay? Process ID. So we need to indicate what process ID there. But here we use mailbox. Okay, that's why we call it indirect, just like the postman. Okay, we send mails, and then we receive mails. You can also maybe put the mail in your mailbox, and then the postman will get the mail and then send it out to the other side. So that means there's a mailbox in between. So it's messages are directed and received from mailbox, also referred to as ports. So that's why I mentioned how you use the ports to indicate the surface. So you have one computer system, so you use different port to indicate the surfaces. Okay, that's also a logic concept. You have a lot of choices to use the port, maybe from maybe 255 to from maybe 100 to 5,000, as long as each of the two bodies know which port you want to use, then that will be fine. And then to establish the relationship between P and Q, each of them have a mailbox, so we establish ID for the mailbox. This ID is just that port number. So that means the process can receive the message or send the message via this port number. Okay, and then the other process also can send or receive message from the same. Then they establish the relationship. Okay, so process can communicate only if they share a mailbox. They share a mailbox, then they can communicate. If they don't share the mailbox, they cannot exchange message information. So similarly for here, properties for this one, for this link. Link established only if processes share a common mailbox. So that means you need to assign a port number to each pair of the processes. And then a link may be associated with many processes. So that means for this mailbox may be shared with many processes. Okay, so this is more flexible. Okay? So that means each process can send and receive a message. And each pair of processes may share several communication links. So they may have different purpose. For example, this is send what type of information. That link is for another one. So they can use multiple mailbox. Okay? That is possible. P and Q, they may have multiple mailbox in between. Okay, and the link may be either unidirectional or bidirectional. So you can allow send and receive both or only one. Okay, this is indirect and direct. Okay, we have these two types, and then okay, compare these two things. Okay, and then let's look at what is the system call now. So that means here we have this things we need to do. Create a new mailbox means create a port number to bind the two processes or multiple processes together, and then allow them to send a message and receive a message. And the next one is send and receive message through the mailbox, and if you finish, you can delete that mailbox. Means you can just delete the port information, do not unbind. Okay? Unbind. So here we use the two system calls. One is called this one, send a message. So message to the mailbox A. Okay? Mailbox A means we send a message to that port number, and then maybe we can temporarily save there, and then there's another process which can fetch data from there, so they can read from that port. So that means the implementation is just like you have a queue. Okay? You have send a message, you may keep sending message, and then another process may keep reading message. Okay, and then receive message. That means you want to get a message because we established this one. Okay, one maybe is the leader and the other one maybe is the member. Okay, send a message to that mailbox. Each one can read maybe after 10 seconds and so on, just like that. So receive a message from the mailbox. So the mailbox will be used to communicate information. Okay, so your process can call this send and receive system calls to get information you want to have or send the information you want to send out. So for here we talk about some problems we want to solve for this indirect communication. For example, 3 processes. We said that we can allow multiple processes share the same mailbox along, for example, like this one, P1, P2, P3, and then maybe we see this one is P1, this one P3. Okay, this is P2, this is P3. For example, if P1 send a message means send it to this one. Okay, send a message here. And then P2, P3 we are just perform the receive. That means this one called the send, this one called the receive. Both are receive. Both, for example, if this is only like a physical mail, so who will get the mail? They will compete, okay? because if there's only one message, if they just remove the message from the queue, right? From the queue. If P1, P2 get the message, P3 will get nothing, right? If P3 get it, P2 will get nothing. So what will the mechanism you want to solve? Who will get the message? It doesn't matter who get it. It doesn't matter as long as one. But the sender don't know who get it, right? So maybe you need to report, acknowledge. Okay. Send the ACK signal to it. So this is a solution. That means we still need to solve this issue. You can allow link to be associated with at most 2 processes. So that means there's no this issue. Okay? You send this to this one or to this one. That means there's only 2 processes. Or you can just allow only 1 process at a time to execute receive. So that means you will not let these 2 to compete, because this is like a shared memory, and each one want to access that shared memory. We need to use, we mentioned before, like a signal, right? Wait signal to see whether this one is free. Okay, if there's already the process which is using this mailbox, other process need to wait. So that means we can also perform like this one. Because this one we can avoid conflicts if both want to access. So who will get the result? Okay? So this one, of course, will only allow one to get it. And then the third one is allow the system to select arbitrary the receiver. So that means maybe generate a number, and then sender is notified who the receiver was. So that means that this one maybe you can just confirm by sending the message. Okay, so I send to maybe to a group of people, and then select one person, 1% to receive, and then after the process receive it, just send a acknowledgement to the sender. So anyway, you need to think about the synchronization issue. This is called synchronization. So if you have this one-to-many, so you need to solve the conflicts. Okay, just for knowledge purpose. And the next one, we talk about the message passing synchronization issue. So next, just a further explanation about this idea. So message passing may be either blocking or non-blocking. So what is blocking? So you can consider a process. Correct? Process, it contains a list of instructions, and then maybe sometime they will send a message to another process, to a queue process, and then queue process will be maybe do something and then receive a message from the P process. So that means beside the send and receive, we have some other option or instructions. So what is the meaning for block? Block, that means when we send a message, we must make sure the message has been successfully received, either by the receiver or has been saved in the mailbox. Before we confirm, we don't continue. That is called blocking. If we don't do like this, we send and then we don't wait for the acknowledgement. We just continue for the rest of the instructions. That is called non-blocking. Okay, this is the idea for blocking or non-blocking. Let's look at blocking is considered synchronous. So why we consider blocking will be synchronous? So that means if we use the blocking, and then we can synchronize the processes. Synchronized process means there's no consistent issue. So we know that means they are adjust according to the piece of each other. So that means if, for example, like we mentioned before, producer consumer, if the buffer is full, you cannot produce another item and then insert. If the buffer is empty, you cannot consume. You must wait for the producer produce a new item and then insert into into the buffer. So this is the idea. So that means we can use this mechanism to implement the same mechanism implement there. So that means the data place is just check the buffer size is full or empty. So here we can use blocking to implement the same thing. Later we will talk about, in fact, we can use this blocking mechanism to implement the producer and the consumer again, and then also have the synchronized processes. So blocking send, that means sender is blocked until the message is received. It can be received in the mailbox or can be received in the other process, depending on whether it's direct or indirect. Okay, if you use a mailbox, that will be indirect. That means the mailbox is, as long as it's not full, and then there's no problem. You can just continue. But if it's full and you need to wait for the consumer, for the other receiver, fetch out one message, and then you can put your message into the mailbox. So that means we always hold the current status of each process. So we don't send a message to a full box. We also don't consume a message from a empty process. Okay? So that means so the receiver process need to wait if the mailbox is empty. So this is called a synchronization. Okay. So in chapter 6 we'll talk about these things in detail. Okay, how to maintain the processes communication in a synchronized way. We have different methods, okay, to implement this one. And then similarly for the blocking receive, I think it's you can use receive doesn't matter. That means just means the operation, okay? Blocking receive operation. So the receiver is blocked until the message is available. If the mailbox is empty or there's nobody send the message to this process, so the producer has not produced the message, so you need to wait. Okay, so this is the idea. So it's blocked until a message is available. Okay, and then next one is non-blocking. This is called asynchronous. Why is it asynchronous? That means you don't block the process, continue to run the rest. So this message may be lost, okay? Because if the mailbox you use the indirect way, if the mailbox is full, you send a message to the mailbox cannot hold this message, and then they will be lost, okay? They will be lost if you don't have any other mechanism, or you keep sending, but many will be lost. So non-blocking sender sends the message and continue the rest instructions. Non-blocking receive, the receiver will receive a valid message or non-message. So you keep receiving from the mailbox. Maybe you got a physical message, maybe you got just empty message. Okay, so that means if the box is full, is empty, you got a null. Null means empty. If you really have a message in the mailbox, okay, you got a message. So that means never wait for other to produce or consume the message. Okay, because the producer with consumer is a very general mechanism for processes collaborations. Okay, so one produce some information, the other one use the information for further processing. And then here different combinations is possible, because here you can find blocking. We have two choices for send and receive. And this one sender also have, you can adopt blocking for send, blocking for non-blocking for send. So 2 by 2 you have 4 choices, okay? But if we both send and receive, we use blocking. We call this is a reservoir. Reservoir means just like the collaborating, they communicate, they meet each other. So send and receive both are using blocking. If both are using blocking, we said this is a synchronous way. That means there's no synchronization issue. For example, the producer-consumer problem will become trivial if we use blocking, send and receive. Okay, let's look at the code. So the code is very easy because the mechanism is there. The send means need to wait Okay, so the producer, so you can find it. You first generate a message, put it into the lec3 produced. So the type of the message called message, that structure type. And then you just keep doing this while loop. So produce the item in the next produce and then send it to the consumer. But this one is already have a mechanism, must wait for the consumer to consume. So that means we must make sure this message has been saved in the buffer or has been consumed by the consumer. Okay. And then similar for here, this consumer will want to consume next message. So we fetch one message from the message queue, and then we just receive it from the message queue. So this one we also do the blocking. If the message queue is already empty, so it will also need to wait. In fact, so that means this one already implemented that wait mechanism, that synchronization mechanism in the two operations. So you can find out now, if we implement like this way, it will be very easy to write. Cut, send, receive. That's only. Okay. So this send will wait for the consumer, and the receive will wait for the producer. If the buffer, if the message queue is full, and the producer will wait. Okay. So if it's full, it will wait. This one, if it's empty, will wait. So that means only these two special issues we need to think about. If there's a common issue, the queue is a lot of empty and also a lot of full. Yeah, you can send producer can send because there's a space to save, and the consumer can consume because there's at least one message to consume. So there's no issue. Okay? And then next, also the final one is like we consider buffer. That means the message queue. Okay? So you can have no message queue, you can have unlimited message queue, you can have also limited size message queue. That's why we have these three types. So queue of the message attached to the link. So for this one, you may have some buffer to temporarily save the message. If it's zero capacity, that means no. You must send a message directly to the other side. So this one is no message are queued on the link. Sender must wait for the receiver. We call this reservoir. Right? So that means must wait for the receiver to consume the message, and then you can continue the rest of your process, because there's no place to temporarily save the message. And the other one is bounded. So that means we have a finite number of message which can save temporarily save the message. So it's if the buffer is full, sender must wait. Okay? So must wait if link full. You can think about link full means that the buffer is full. And then unbounded capacity. So that means that potentially you don't need to consider the size is very big. So that means usually you will no chance to exceed that limit. So you can consider that the infinite many items for you to save the message. So that means the sender can always send a message and save into the buffer, but receiver still need to wait if the buffer is empty. Okay, so that means the receiver will wait if the buffer is empty. We can add a sentence below. Okay, this is the final slides for this instructor video. We'll look at the quiz. Okay, for here. So the first one is a blocking send and a blocking receive is known as what? So that means both send and receive we use blocking. That will be synchronized message, reservoirs, block message, asynchronized message. So it's not a message cut, it's a reservoir. So that means both will send, then it's a synchronized way. Both will block, both will block. Next one, in a temporary queue, the sender must always block until the recipient receives the message. Must wait, always wait. So there must be 0 capacity. Okay? And then next one, under indirect communication, each process that wants to communicate must explicitly name the recipient or sender of the communication, true or false. So this one we mentioned about the indirect communication. And then each process need to indicate the name. Indirect is using a mailbox, and then direct communication will name the process. So this is just the reverse way. We must get rid of the in. So it is indirect. It is direct. We must name the recipient or the sender. So that means send to a recipient message, a message, or you receive a message from a B. So like that one. So this is direct. So indirect, we don't need to do that. So it's false, 0, and the reservoir. Okay. So next week we'll continue with some example IPC. So I only want to mention about this one. In this section we already talked about the pipe as well. In fact, the idea is simple as well, since we already talked about the message passing. So this is just like the message passing. So implemented in the Linux, and then in your programming assignment 1, it mentioned about the pipes as well. So if you already reached that part, you have reached that coding part, and then you can just have a look in advance, because I think we already covered the most knowledge part. Now is only all the knowledge part. Now is only the examples. So this is like the examples in example IPC system in different operating systems, and this one is about the CSC distributed system, or their communication, okay, based on socket. So overall, this chapter has been finished in terms of the contents, main contents, and the rest will continue with some examples to enhance your understanding. Okay, we'll see you next week, and then have a nice weekend.